All right. So today we're going to actually begin the meat of the spectroscopy lecture, which is dealing with NMR. And we're going to talk about that. You've seen this before. If you took lab at any point in the last 2 years, then part one, organic one lab at any point in the last 2 years, you've seen this already somewhat. So NMR is short for nuclear magnetic resonance, and it really gives us 4 things about a molecule. And again, this is the absolute most definitive way to prove a structure. Like whatever you made, this is the absolute most definitive way to determine that you have what you say you have. So it tells us a few things. It tells us how many non-equivalent hydrogens are present. So that's going to be reflected in the number of signals that are present in the spectrum. And then it also tells us whether those hydrogens are in electron-rich or electron-poor environments. That's going to be reflected in where they are on the spectrum, upfield and downfield. So upfield is more electron-poor, going towards 0. And then downfield is more upfield is more electron-rich, going towards 0. And then downfield is more electron-poor, going towards 10. And then it also going to tell you how many of each hydrogen is present. So NMR is very, very precise and it's very specific. Unlike infrared, which is general, right? You know that there's a carbonyl present, but you don't know whether it's an amide or an aldehyde, or ketone, or an ester. So you really don't know that, right? So you'll know how many of each type of hydrogen is present, and then how the molecule is constructed, right? You can tell that by what we call the splitting pattern, like how many lines a particular signal is split into. We're going to talk about each one of these things independently. So NMR, there are different types of NMR that you can do. The magnet that we have, you can do proton, fluorine, phosphorus, and carbon, those 4 nuclei. But really, you can do basically at this point, you can do many, many, many different nuclei you can study by NMR, because the technology is so far advanced than what it used to be. Like you could basically study any nuclei on the periodic table, right? If it's present, there's a probe that can study it. But again, the probe that we have at Tuskegee, it's a quad nuclear probe, so it can study 4 different types of nuclei. All you have to do is tell the receiver what experiment you want to run, and you can do that. All right, so again, when you talk about construction, how things are put together, you can determine that by how the signals get split. So like you can see this signal down here between 7 and 6 is split into 4 lines. And we're going to talk about how you're able to determine how many lines each signal should be, so on and so forth. You can see down here at 2, that signal is split into 2 lines. And then the rest of these signals are split or not split. They're all single lines, right? So based on this spectrum, there are 1, 2, 3, 4, 5 signals. And because there are 5 signals, that means that there are 5 different types of protons in this molecule. And so if you look at the molecule itself, you have a CH3 here. So these hydrogens are going to give off a signal. These 2 hydrogens on this carbon are going to give off a signal. These hydrogens will give off a signal. So will these. And then this hydrogen right here is also going to give off a signal, right? So, and those signals show up in different places because, again, they're in different chemical environments. They're in either electron-rich or electron-poor environments. So NMR, I kind of already ran this down, but it's short for nuclear magnetic resonance. And so the way it works, every hydrogen atom has a pre-existing magnetic field around the nucleus. And so that pre-existing magnetic field, if it's acted on by an external magnetic field, then you're able to generate a signal based on excitation of the field and then relaxation of the field. I'm gonna show you how that works in a second. But also what it tells us about, again, the carbon hydrogen framework. But again, you can do other types of NMR. Today, we're only talking about proton NMR, but you can also do carbon NMR, where you're studying the nucleus of carbon. You can do, again, fluorine, oxygen NMR, deuterium NMR, phosphorus NMR. Like, there's so many different types of NMR that you can do. The spectrum itself is from 0 to 10, and everything is relative to the chemical shift of TMS, tetramethylsilane, which is a silicon with 4 CH3 groups around it. All those hydrogens on that TMS molecule show up as 0, right? So you can basically calibrate any NMR spectrum based on the chemical shift of TMS, which is always 0. So you've seen this before. If you've been down in the NMR lab in room 101, right? It's basically just a giant superconducting magnet. And the way you run your sample, you dissolve it up in a deuterated solvent, like deuterated chloroform or deuterated acetone or water. And then that goes into the NMR tube, which is pictured right here. And you sit that in a spinner, sit it down in the magnet, and drop it down into the instrument. The key to the instrument is the RF energy, right? There's a radio frequency pulse that irradiates your sample. And that's the pulse that acts upon the magnetic field of whatever nucleus you're studying and excites it, and then it relaxes back. So let me show you in kind of rudimentary terms. So each one of these is a nucleus. And what happens is those nuclei, the magnetic field is what we call precessing or spinning, but it's doing so at random, right? And then you apply the magnetic field to it here, and then some of those line up with the field. Some of the protons line up with the field. Other proton nuclei, the spins of the magnetic field line up against the applied magnetic field. So then they're no longer random. They're either going with the field or against the field. So the ones that are going against the field, you basically pulse them with radio frequency radiation, and they line up with the field, right? But they don't stay. So they line up, and then they relax back to their original state, and then they keep doing that. And depending on what kind of experiment you're running, the normal proton NMR experiment is 16 scans. So you'll pulse this thing 16 times. So it'll line up, then it'll relax. It'll line up, and then it'll relax. And then after which you generate what's called an FID, which is this weird looking graph of, where's my cursor? This weird looking graph over here. And then you do a Fourier transform. That's not something that you have to do. That's something that the processing software does. And it converts the FID into a spectrum, right? It sounds simple, but it's really like some high level mathematics happening there. But at any rate, the FID picks up the energy release from the decay, right? So the excitation and then relaxation, every time that happens, energy is given off. And so the FID picks that up. And then you're able to convert that into a readable spectrum where every one of your protons has a specific signal, right? So let's look at a couple of things. Let's look at an example. And in this example, we're going to look at some of the different characteristics of NMR, basically the number of signals that are given off and the location, not given off, but the number of signals that are detected. The location, meaning of the chemical shift, whether it's at 0 parts per million, 5 parts per million, whatever, upfield or downfield. And then we're going to look at the multiplicity, because it's that part that gives you an idea about the connectivity of which hydrogens are next door to which in a molecule. So that's how, if you're doing NMR, you can even determine, that's how you can use NMR to determine the structure. If you do the NMR and the infrared and use those things together, plus do what's called determining the degrees of unsaturation, those three things, you can figure out a structure from any NMR. That may be, if it's something huge and super complicated, it may take more time, but regular, like small molecules that don't have a bunch of different protons, those are fairly easy to elucidate if you have the NMR and have some other spectral data. Right, so you see, if you watch the video, you saw this already. So when we talk about, this is ethyl acetate. If you see here, you got 1, 2, I color-coded the protons, right, on purpose. So there are 3 different types of protons. None of them are equivalent. And so what that means is that I'm going to get 3 signals, right? And you can see in the NMR that I have 3 signals, and they're not all in the same place. Some of them are upfield, some of them are downfield, right? But they are there. And they're not, if you look at the spectrum, they don't look the same either. This signal is split into 3 lines. This signal is split into 4 lines. This signal is not split at all, right? So when you look at this, this is a really basic NMR, but it gives you a lot of information. It tells you which protons are in electron-rich environments, which ones are in electron-poor environments. It tells you which ones are next door to one another, and all of that you can determine from this spectrum. All right. So that I like to call the different types of proton sets, because these 3 are equivalent to one another, but they're not equivalent to the other 2 sets of protons. Just like these 2 are equivalent to one another, but they're not equivalent to the blue or the red sets of protons. And then these red ones are the 3 on that carbon. They're all equivalent to each other, but they're not equivalent to the other 2 sets of protons here. All right. So the way you determine equivalence is to take one of those protons off and replace it with another atom. And then take, if you, the set that you wish to compare, the set that you want to compare, you would remove one of those 2. So you take, if let's say we wanted to compare these 2, I would take one of these off and put a chlorine there. And then in the second structure, I would take one of these off and put a chlorine there. And if they are identical, then the protons are equivalent. If you get 2 different compounds, then they're not equivalent. And you can obviously see that if I put a chlorine here, and then I also had a structure where the chlorine was here, that's not the same. Those are 2 separate, those will be 2 isomers of one. And so that's the test for equivalence. So if you go to here, you can see if I want to compare these 2, I could put take one of these protons off and put a halogen there. It doesn't matter what atom you use. And then I could take one of these off and put a halogen there and compare them. If I get the same thing, then I know that they are equivalent, or what we call homotopic. If they're not the same, then the term that we use is heterotopic, meaning that they are non-equivalent. All right, any questions about that? All right, so let's look at some other examples, right? So you can see in this first example, we have 3 sets of non-equivalent protons. None of these hydrogens are identical, right? So these 3 are the same, identical to each other, but compared to the other 2 sets of protons, they're different, right? So you got 3 sets of non-equivalent protons. How many signals should I get?
3.
3 signals. right? Because every set of protons that's non-equivalent is going to have its own signal. Right here, same thing. I have a CH3 here, and it's really important to understand if this thing is not symmetrical, then it doesn't matter that that's a CH3 and that's a CH3. If it's not symmetrical, they're not going to be the same. You're going to get two isomers if you compare them. How many sets of protons are here? We know that that's two right there. The CH3s, that's one. So that's two sets. What else do we have?
I think it's 7 total.
7. Let's see. Yes. So you got a CH2 here, a CH here, another CH2 here, and a CH2 here, right in here. None of these are the same. You could do the test for equivalence by replacing each one systematically. One, replace that, all the way down the chain, and you'll see that when you compare the structures, none of them are identical, right? So you're going to have 7 signals for this molecule. So if you got 7 types of different protons, then you're going to have 7 signals. Every signal is going to generate its own specific, or every set of protons is going to generate its own specific signal. But equivalent protons are going to be represented by the same signal. So these two are equivalent to each other. So they're not going to have separate signals. It's going to be one signal, and that signal is going to represent those 2 protons. Right? Let's do the next one. What about here? What do you think? So you got a proton on each carbon in a double bond. Then you have a set of protons here, here, 1 here, 2 here, and 2 here. Right? So that also is going to give you 7 signals. Right? So in the NMR spectrum, when if you took an NMR of this compound, you would get 7 signals that show up at different places on the spectrum between 0 and 10. And that spectrum from 0 to 10 is measured in parts per million. Right, so here's the spectrum for that. Right, and this is the spectrum for this molecule. You can see we said 7 signals, so 1, 2, 3, 4, 5, 6, 7. Right, so that's 7 signals for that. And this signal right here, I wish I could zoom in on that. Okay, I got it. So you can see these are really, really complex right here, right? This is a really complex splitting pattern. And because of that complexity, and because of the fact that the chlorine here could be a chiral center, that's why you see this weird splitting right here, right? Because it makes it, if this is chiral, which I don't have it shown as chiral, but if it's chiral, then that's going to have an effect on this set of protons as well as this set over here. But we'll talk about that later. It's going to lead to what we call complex splitting. But I don't want to talk about that right this second. So now let's talk about the multiplicity or splitting pattern. Right, so we already know we're going back to ethyl acetate, back to our simple example. And we can see right here, how many lines is that signal split into? Where I have the cursor. Can y'all see my cursor? How many lines is that split into?
4.
4. Good. What about here?
3.
Mm-hmm. And then this is not split, right? That's on purpose. If you look at the structure of this molecule, right? I'm gonna start with the 4. That 4, we call that, you can write this down, we call that a quartet, right? It's split into 4 lines. What that means is that whatever that set of protons is, it's got 3 protons adjacent to it, on the carbon adjacent to it. So if we look over here, right? The color code says that it's the pink protons. So that set of protons, if you look to the left, there's a CH3. If you look to the right, there's no protons here on oxygen, right? And so the way we determine the multiplicity or the splitting pattern is simple. We use what we call the N+1 rule. So N would be the number of neighbors plus 1. So this set of protons has 3 neighboring protons on the carbon next door. So N will be 3, and then N+1 will be 4. That's why this is split into 4 lines. All right, questions about that? That's why that's split into 4 lines, because it has 3 neighboring protons adjacent to it, on the carbon adjacent. All right, let's do the red protons right here. How many hydrogens are on the neighboring carbon? Right here. How many hydrogens are there? Or are there any hydrogens there?
Would it be 3 since the CH3 or
No, we're looking at these.
then none?
None, exactly. So N, in this case, for this set of protons, N will be 0, right? So N is 0, N+1 is 1. I mean, yeah, 0 plus 1 is 1. And so, boom, it's going to be here. That's what we call a singlet. It's one line. It's not split. All right? So it's a singlet. And then we look at the blue protons. How many neighbors does the blue set of blue protons have?
2.
2, right? Good. These protons, they see these 2 protons up here on this adjacent carbon as neighbors. So N for this set of protons is 2. So N+1 is going to be 3. So that's going to be split into a triplet, right? So that's what you see right here, 3 lines. That's called a triplet. So you have a triplet, a singlet, and a quartet, right? So this is again how you can put a structure together from an NMR. If you see a quartet, then you know that however many protons that's representative of, that set of protons is neighbored by a CH3, right? Or neighbored by 3 protons. Same thing here. If you see a triplet, then that's telling you that that set of protons is neighbored by a carbon that has 2 protons on it. So if you have the splitting patterns and you have the chemical shifts and you have what we call the integration, which we're going to talk about in a second, in other words, how many protons each signal represents, with those 3 things and a little bit more spectral data, you can come up with a structure to match the spectrum, right? So we already talked about this. So the N+1 rule, right? Again, if it's a quartet, that means it's neighbored by 3 protons. If it's a triplet, that means it's neighbored by 2 protons. And if it's a singlet, that means it has no neighbors. So N is 0 and N+1 is going to be 1, like that. So this is how you determine the splitting pattern of any set of protons. Now, it's not always this simple, because sometimes you have complex splitting, especially if you have stereocenters present in a molecule. Then you're going to get complex splitting, because some of your protons that normally would be considered equivalent become non-equivalent. But we'll talk more about that later. Right, so this is why you see that. This is Pascal's triangle. And so if if we have neighboring protons, right, the set that you're looking at for the signal is experiencing the magnetic field of the neighbors, right? So if it has 2 neighbors, it's going to experience that magnetic field in 3 different ways, right? It's going to, the magnetic field will either be both against the field, both with the field. That's what the 1 and 1, and then the 2 in the middle is taking those two magnetic fields and alternating them. So one with and one against. And then here you can see the top arrow is going the opposite direction. So one with and one against. So that is what a triplet looks like. And that's why if you look at the triplet, the middle line is higher than the two outer lines. That's the reason for that. It's because of how that set of protons is experiencing the neighboring protons' magnetic fields, right? And this works for any molecule, right? And if there's complex splitting, then the model changes a little bit, but it's still based off the n+1 rule. All right, let's talk about the locations. All right, for chemical shift, that's going to be determined by what we call the chemical environment, meaning if the protons are electron rich or electron poor, right? So if you look here, which one is the furthest down away from zero?
Quartet.
The quartet. So that quartet is all the way at 4 point something. We say that it's further downfield. And then the one closest to zero is the triplet, which we would say is further upfield. Now look at the color coding. Like so quartet is for the pink protons, the red protons are the singlet, and then the triplet, that's the blue protons. So why do you think the quartet is so far downfield? What's so special about it? All right, if you look at what's around it, that's actually connected to that carbon is an oxygen. And we know oxygen is very electronegative, right? It has the second highest electronegativity of all of your atoms on the periodic table. Fluorine is first and oxygen is second. And so oxygen, being electronegative, it does what we call, and you should write this down, it does what we call de-shielding, right? De-shielding.
Is that like the same thing from what we did on the assignment? Because I remember seeing de-shielding.
It is. Yep. So oxygen de-shields protons. In other words, it lessens the electron density around that set of protons. And anytime a set of protons is de-shielded, its signal is gonna move downfield. Right. Anytime you de-shield a set of protons. So if you put a set of protons near an electronegative atom, the signal is going to move further downfield because those protons are going to be considered electron poor. Right. And if you look right here, the blue set is the furthest upfield, right? Because it's further away from the oxygen and further away from the carbonyl. And then the singlet is kind of downfield as well because it's on a carbon right here that's next door to a carbonyl. And you know the carbonyl itself is got a big dipole going towards oxygen. So that's also de-shielded, just not as much as the oxygen, right? So if you de-shield a set of protons, it's going to move the signal downfield, right? Because the electron density around those protons is going to be decreased because of the electronegativity of the atom that they're bonded to or that they're adjacent to. All right, so this right here, I gotta take this off. Right, so this is a chart basically of some common chemical shifts, right? So alkyl protons with no electronegative atoms, just carbons and hydrogens from 2 down to 0. That's where they normally show up. The minute you stick a sp2 hybridized atom next to that set of protons, it de-shields it. Because remember, for hybridization, sp2 is a little bit more electronegative than sp3. And then sp is more electronegative than sp2 because as the percent S character increases on a hybridized carbon, so does its electronegativity. So if you stick a sp2 carbon right here, then boom, that goes, now it shows up between 2 and 3. And you can see that here, right? This is almost, I mean, say 2.1, 2.2. And that's this red set of protons right here that's adjacent to, on a carbon, adjacent to a carbonyl, right? That's why it shows up here. And again, this chart, knowing the locations of certain types of protons and what functional groups move them, you know, downfield or upfield, that also helps you to determine the structure, right? Because if you know that at 2, that's some type of allylic proton, right? Then it can be adjacent to a carbonyl or adjacent to a double bond. Then if you looked at the infrared, you could tell, well, there's a absorbance or spike or signal at 1615, right? Reciprocal centimeters. So that wouldn't be necessarily a carbonyl, but it could be a double bond. So there's a way to interpret all this stuff together in totality to determine the structure. All right. If it's adjacent to oxygen or nitrogen or halogen, then the shift is going to be somewhere between 3 and 5. Right? If it's directly attached to a double bond, it's going to be between 4.5 and 6.5. These are called vanillic protons. They're right on, they're attached to the double bond. This aromatic protons between 6.5 and 8. And then between 9 and 10, your aldehyde protons, and then your carboxylic acid protons will be past 10, somewhere between 10 and 12. When we made aspirin, you could see all of this. You could see the aromatics, you could see the carboxylic acid protons, and you can see these allylic type protons as well, because all of that was present in that aspirin molecule. All right, any questions about location, splitting pattern, or number of signals? Because that's what we've talked about so far.
No, sir.
Right? So those 3 things are the 3 basic things that you'll get from an NMR. The location tells you, again, if it's electron, the protons you're looking at are in electron-rich or electron-poor environments. The splitting pattern tells you how it's constructed, what's next door to what. And then the number of signals tells you what's equivalent and what's non-equivalent. All right, so let's look at an example. This is and if you had a problem like this, typically what you would get is the formula, so you can calculate the degrees of unsaturation. You get the molecular weight is not necessary, or the mass spec, but you have molecular weight. This is the mass spec analysis, and then your infrared, you got peaks at 2975, 1675, 1500, and 1100. What do you think that 1100 corresponds to in the infrared? Which bond in here is that indicative of? It's the CO6 single bond. So this bond right here, it's a really sharp stretch at 1100. What do you think 2975 is?
Wait, what do you mean? Oh,
In the infrared, like what functional group shows up at 2975? If it was a really raggedy, jagged looking stretch, strong stretch at 2975, what would that be? Right, you see all these carbons in this alkyl chain, that's alkyl stretching. All right, so we took this reaction, we did it. Now we got proof that we have it. So you can see right here. Now these 2 sets of protons I have them the same color on purpose because they will be equivalent. Right? If I replaced either one of these with another atom and compared the 2 structures, I'll get the same thing. Right? So that's a signal. That's one signal right there. one signal. And then each one of these, because there's no symmetry, each one of these is going to give off a signal. So that should be a total of 1, 2, 3, 4, 5, 6 signals. Let's see if we see that down here. 1, 2, 3, 4, 5, 6. So we got 6 signals in the NMR. Now we just need to figure out which one is which, because that you have. How would you do that? What are we looking for to determine the connectivity? Like what is next door to what? How do we figure that out?
Whether it's a quartet or a
Yes, we're looking for the splitting patterns and the location. Because if this is what we made, we know what we're looking for. Now we just need to confirm it, right? Nobody goes into a lab blind, just pouring stuff into flask and waiting to see what happens. You have a plan. You say, I want to make this molecule and I want bromine at this location, and I'm going to do this reaction to do it. And then so now you have your product, but you need to confirm it. So let's start here, right? That set of protons, the black set, what would the signal look like for that? Would it be a singlet? Would it be a doublet, a triplet, a quartet, pentet? What would it be? What do you think? And how do I determine that?
Are we starting upfield or downfield? Are you talking about the
Right here.
CH3?
We're looking at right here.
That's going to be single. What do you
A
call that?
singlet. Because on the atom, you're right, on the atom next door, there are no protons. So this is going to be a singlet, and it's on a carbon that's bonded to oxygen. So is it going to be upfield or downfield?
Upfield.
It's bonded to
Wait.
oxygen, which is going to de-shield it.
Okay, so downfield.
So it's going to be downfield, right? So we only have 2 singlets in the spectrum. We got a singlet here, and we got a singlet here, right? Now, if you look at them, they're also different heights. This one is about half of this one. So we're going to talk about that in a second. I'm going to weave that into this discussion, right? So the black set is here, right? That CH3 is represented by this signal. Are y'all following that? Does that make sense? And then now let's look at go ahead. Does somebody have a question?
Yeah, I was just gonna. So there were 2 singlets, but based off of the fact that it was connected to an oxygen, you chose the one more downfield.
Or downfield, yes.
Okay.
All right, good question. Let's look at the other one that's a singlet. It's the red protons right here. If you look at this carbon, are there any hydrogens here? Because see, this gives us a chance to answer another question too. Because somebody is thinking that this shouldn't be a singlet because of these 3 protons over here. But if you look at the structure, there's a carbon between those 2 carbons. So they're not going to split with one another. Like, so unless there's a proton on the carbon right next door, there's not going to be any splitting, right? So here, there's no hydrogen. So what is N for this set of protons if there are no hydrogens adjacent?
It is 0.
N is 0. And then N plus 1 is going to be what? 0 plus 1, which will be 1. So it should be a singlet. All right, now let me add in another piece of information right here. And that is integration. Right? The integration tells you how many protons each signal represents. So it's basically, I have here the number of protons per signal. All right. So how many protons is this signal, the black one, representative of? How many hydrogens are here?
It should have any protons. What?
This signal is represents. Right. How many hydrogens are here on this carbon?
3.
3. So this signal, when we integrate it, and by integrating, you basically take, you put a curve over it like this. It's raggedy looking, sorry. And then the area under that curve, which is determined by the processing software, it's going to tell you how many signals this represents, right? So this would integrate for 3 protons, this signal. All right.
So question.
Go ahead.
So we don't count the other hydrogen bonds,
Which other ones?
or like, because I'm seeing like the different, like the pink and like.
Everything is separate.
Okay.
Everything is, that's a great question. Everything is separate. So let's look at the red signal. Let me see if this is going to make it click for you. So you got 3 here and 3 here. Is that right? And they're all equivalent. So what's the total? How many protons should that signal represent? Yep, these 3 and these 3 are equivalent. And they're all represented by the same signal. If I integrated that signal, basically taking the area under the curve. Sorry about that. It's raggedy looking, but you get the point. How many protons should that be? Should that signal represent?
Are we adding them, or
Yeah,
so it'd be 6?
6. You add them together. So the integration for this signal is going to be 6. Can you see now why this is double the height of this? Because this represents 3 and this represents 6. So the intensity is going to be different. And the reason this is representative of 6 protons, again, is because these 3 and these 3 are not going to give separate signals because they are equivalent to one another. They will be represented by the same signal. So that's why there's one signal here that integrates for 6 protons. So the integration tells you how many of each type of proton is present. The number of signals tells you how many different types of protons are present. So how many sets are present, right? And then the splitting pattern tells you how they're connected, how they are related to one another. All right, questions about that?
No, I don't have any questions, but yesterday I watched a video about how helium cools the NMRs, the magnet and the NMRs, and also MRIs.
Yes.
And how it's running out.
You mean helium?
Yeah, helium.
Yeah, we definitely have a shortage.
Yeah, and I was wondering if Tuskegee does any research on superconducting metals. Well, no, yeah, that will have a higher heat capacity or something.
Yeah, probably they may be doing something like that over in the material science and engineering program. That's a great question. But yeah, the helium shortage, we've been hit by that because to fill our magnet, it costs we have to fill it once a year, and it's like 5,000 every time they come out. And the price keeps going up because the amount of helium it just keeps decreasing. For whatever reason, there's been a shortage for the last several years. And then now they make NMR magnets that are what you call cryo-cool magnets. So it's like a closed system, and you don't have to fill it as often. At least that's what the theory is behind it. You still lose some helium, but they make these closed systems where the helium just continues to recirculate without needing to be refilled. So you don't have to use as much, but even that you have to fill it at some point or refill it. It's just not it's called a low boil off magnet. So the amount of helium that boils off or is released is much less. But yeah, you may want to talk to Dr. Curry because he'll know exactly what's going on in the MSEG department. But I'm not sure if they're studying superconductors or not. That's a great question, though. And MRI is basically very similar to NMR, right? It's just a big freaking magnet. Super cool with liquid helium and liquid nitrogen. But the imaging that it does is different. Right? Questions? Any questions? So integration, how many of each type? Number of signals, how many different types of protons, and then the split pattern tells you how they're related, how they are situated as related to one another. All right. Did everybody get this down before I clear it off? What's time to stop? All right. We're going to pick back up with this example on Friday, and we're going to start working through the examples in that handout. So if you don't have the handout, make sure you bring it with you on Friday and download it and bring it with you. I'll upload this PowerPoint to Blackboard.